So to begin with, I'm going to give a little bit of background about the solar system and objects that we talk about in the solar system. We're generally talking about solar system small bodies, and these are classically defined into two different categories. We have asteroids, like 4 through 3 arrows here. These objects are rocky. As you can see, that's just a sort of potato-shaped rock. And they appear in images as point sources. So they just look like a dot on the sky. They also happen to have orbits relatively close to the sun. And this is because if they are too far out, then ice can form on their surfaces, and you get the other object, comets. Comets are, like 103P Hartley, are about the same size. These are usually about half rock, half ice. And as they get close to the sun, that ice tends to sublimate and produce these beautiful eponymous coma as dust gets streamed off the surface. And because of that, if you look at them in images, they tend to have sort of fuzzy comae around them. But this is the classic division, and as science gets more advanced, all of these dichotomies must fall. And so in recent decades, we have found several new populations that start to undercut this dichotomy. So this is an example here. This is Elst Pizarro. You can see Elst Pizarro right there, and this long tail coming off of it, and I'll do the similar thing over here. There's the object, there's the tail. And the fact that it has this tail is quite interesting because it's in the main belt, the main asteroid belt, and we would expect it, based on its composition, to look like to be an asteroid, but it still has this activity. And as we talk about these new objects, I'm going to be talking to you today about a new population of these objects that I was involved in the discovery of, which are the dark comets. Dark comets are small near-Earth objects, so they have orbits that come relatively close to the Earth. And they have, because they're relatively close to the Earth, they should be asteroids. And they look in images like asteroids. Here is one of them. This is 1998 KY26. There's the object that's circled, and there's not really any coma around it. There's not that sort of fuzzy cloud that you would see from a comet. However, despite that fact, they do have very significant non-gravitational accelerations. And that means that they are moving through forces beyond gravity. Comets do this all the time. As you can imagine, if you are blasting material off the surface, that is a mini rocket, and so it gets to move. But you would not expect to see that for an object that has very little coma. Now, there are effects that can cause non-gravitational acceleration on comets. Radiation pressure is one of them. The light of the sun will push the objects in a certain direction. There's also the Yarkovsky effect, which is somewhat nasty, and I can get into later, but it can also operate on asteroids. The thing that we get that's quite interesting, though, is that non-gravitational accelerations, like the radiation pressure, have very particular forms. Radiation pressure pushes you away from the sun. It does not push you perpendicular to the sun. That's not how radiation works. And so because of that, you expect it to be in a specific direction along the orbit, which is called the A1 direction, which is radial. We also expect it to have a certain magnitude, which is shown here in this pink line, and all these little pink dots are objects that have known radiation pressures. And that magnitude is supposed to scale with the size of the object. The Yarkovsky effect is supposed to go along the direction of the orbit, the A2 direction, and it has a much lower magnitude, which is shown by this dark blue line, and these are all Yarkovsky effect asteroids. The dark comets are shown here as these diamonds in orange and purple. The orange diamonds are in the out-of-plane directions. These are out of the plane of the orbit. The purple diamonds are along the direction of the orbit, in the direction of the Yarkovsky effect. But what you can see from this, just sort of right off the bat, is that it tends to align with a radiation pressure effect, and is far too high magnitude to be a Yarkovsky effect. And the thing that's interesting is that it's the wrong direction to be radiation pressure, and way too large to be Yarkovsky effect. And the only explanation that we really have remaining is that it's some sort of sublimation like comets. Now, moving on from this, we can actually look at these objects in more detail and study their orbits. And what we find as we discover more and more of these objects is that there's actually two populations of them. There are currently 14 objects in total. Some of them, which are shown here in these red ellipses, are what we call outer dark comets. And these are objects that are high eccentricity and are relatively large semi-major axes. This maroon circle here is Jupiter, and this blue one is the Earth. And you can see that they pass close to the Earth, but they also move out quite far to Jupiter. However, there's also dark comets, the inner dark comets, shown in here in gray and also in here in gray, which come close to the Earth but are on relatively circular orbits. And these two different populations are an interesting thing that we can start to look at as we try to piece out what these objects are and where they came from. So the research that I've been doing is looking at the origins of these objects, and I believe we've identified a plausible origin for how these objects are where they are and why they have the properties, the anomalous properties that they do. So what we do is we do simulations. We take a bunch of near-Earth objects from all the different places you could get a near-Earth object. We add non-gravitational accelerations, and then we run large-scale simulations of millions of objects and see where they end up. And what I'm showing here is the heat map is the probability of finding an object from the Jupiter family comet population in this location. And these diamond plots here are the inner dark comets, and these circular ones are the outer dark comets. There's 5. The 5th one is hidden behind that 4th one. And what you can see here is that the Jupiter family comets, which are comets that orbit somewhat close to the orbit of Jupiter, are relatively consistent with where you would expect to find these outer dark comets. But there is 0% chance that you find an inner dark comet at this location. It's just not possible to find an object there. So we think that then these are probably Jupiter family comets, while these are something else. And the interesting thing is that that something else is the inner main belt. This is the same distribution, but for inner main belt objects. And what you can see is that these are somewhat lower probability, and these are also relatively low probability, but that probability is not 0. And one of the things that you have to do when you do these simulations is that these are just the number of objects. It does not tell you how likely you are to discover it. And you are obviously more likely to see an object close to the Earth. And so while the probability of finding an object here is small, the probability of detecting an object here is far larger than here, and so we find all these objects in this region. But this is very interesting, because if we say that the dark comets probably have ice on their surface that is causing this outgassing, and they're from the inner main belt, that suggests that there could be reservoirs of ices in the inner main belt. The inner main belt is interior to what we call the ice line, and so ice cannot survive on its surface for the age of the solar system. These objects either have to be hiding ice in their interior or have been put there more recently. It's very hard to put things there very recently. They're probably hiding ice in the interior. And not only that, the fact that we have this volatile reservoir in the inner main belt and the fact that they can get close to the Earth means that these objects could play a role in delivering water and other volatile species to the Earth. The Earth is formed too close to the sun for water to have formed locally on the Earth. It has to be delivered from somewhere further out in the solar system. We would originally think, and I don't have slides for this, but I'll just say this. We originally think that the water from the Earth is from Kuiper Belt objects and perhaps from Oort cloud objects. But the problem with that is that the deuterium to hydrogen ratio of Earth water does not match those asteroids. It does match things from the main belt, but we don't have a good convincing mechanism for how those main belt objects could get to the Earth. And so what the dark comets do is they provide a new population of ices that we can study that have demonstrably been able to get close to the Earth, could have been impactors, and that can preserve ices over the age of the solar system. Now, based on all this, we can then start to suggest an evolutionary track for these dark comets, in particular for the inner dark comets. The outer dark comets are much easier. You just kick a Jupiter family comet in, but these are quite interesting. So I'll go through this in time. We start with a Jupiter family or main belt comet with a semi-major axis of about 3 AU and a pretty low eccentricity. It then gets kicked into the near-Earth environment. This is done through various gravitational effects. The outer planets put hard limits on where asteroids can be in the inner main belt, and as diffusion moves asteroids around, they can fall into one of those gaps and get kicked out into the near-Earth environment. At that point, it will then begin to spin up. It will spin up as either volatiles on its surface escape, which causes it to spin up, or through things like the Yorp effect, which is a radiation pressure effect that can apply to asteroids that spins objects and makes them spin up. And as it spins up, it will eventually spin so quickly that it cannot hold itself together with either gravity or its own material strength, and so it tears itself into pieces. As it does this, it does a couple of things. It will continue to spin up, and it will expose the interior of the asteroid. And if we have ice in the inner main belt, it must be stored in the interior of the asteroid. That is, you can show that there can be ice preserved there over the age of the solar system, but not on the surface. And so as you tear these objects apart and you expose that interior, that ice is exposed to the surface, and it begins to sublimate and drives this process faster and faster. This will eventually lead to a disintegration cascade. You tear an object apart, those pieces spin up, they tear themselves apart, this continues. And what we eventually end up with is some objects like 1998 KY26, the dark comets that we're talking about, which are small, rapidly rotating, they have odd densities, and they have these, albeit weak, non-gravitational accelerations from these ices that we have exposed. Now, there also are possible final states. It can either continue this process to the point where it tears itself into pieces completely, which we have seen in all sorts of comets, or it can lose its volatiles around this point and stabilize to a final devolatilized state. And what's interesting is that we found several objects like this, like 2009 BD, which have densities that we would expect from comets, but are in the near-Earth environment, are small and rapidly rotating, and don't have a clear explanation. Asteroids are usually much more dense than this. So this is our understanding of where these things came from. And based on this, we can then do some calculations and say that there must be many more of these objects. The fact that we found 14, you saw in the original graph that that is a very observationally biased sample. And this process should make many of these. And if you calculate this from observations alone, you get estimates, and this is a terrible range. There's somewhere between 0.5% and 60% of near-Earth objects with dark comets. I understand this is terrible. This is the best we can do with the current observations. We don't have good uncertainties on anything, and so this is what we're stuck with. 60% is quite a lot. 0.5% is still 10,000 objects. So it's quite a few regardless. And even if we're 0.5%, this is still a significant population and a good amount of mass in the near-Earth environment. Now, there's lots more work to do. We're expected to discover a lot more of these in the future. We are very lucky that about, 3 weeks ago, the Vera Rubin Observatory came online. This is its first light image. In its first 10 hours of observation, it found 2,000 asteroids. It will be running for 10 years. So and those detection rates will go down because I found all the easy ones in those first 10 hours, and it'll find all the easy ones in the first year, but we're expecting to find lots and lots more asteroids with this survey. Gaia, which is a ESA mission to look at astrometry across vast swaths of the sky at billions of objects, will also find more of these. And then the NEO Surveyor mission is a space telescope that NASA is building specifically to find near-Earth objects. And given the likely large population fraction that these objects have, we're expecting to find a lot more of these as these systems come online and as we get more and more data. But there are also issues with all these surveys, which is that they rely on linking objects across apparitions. The way that you find a non-gravitational acceleration is you look at an object for a week, and then it goes away, and then you find it again 10 years later. And 10 years later, it's in a slightly different position from where you would expect it to be if it just moved with gravity. And we have to fit an orbit through that, and if you can't fit an orbit, you have to add non-gravitational accelerations to make those observations match up. But you need to see an object and then see it again 10 years later and know that it's the same object. And if your non-gravitational accelerations are very large, then you will move quite a bit on the sky. And if you say, okay, I expect to see an asteroid here, and I saw an asteroid here, you're not necessarily going to say, these are definitely the same object. If it's moved by, if you see an object, if you see an object here, and then it's actually in a different location, you're going to say, probably a new object, not necessarily the same one. And so what this means is that non-gravitational accelerations and objects that are moving in non-gravitational trajectories are more likely to be missed by surveys. And that means that the larger the non-gravitational acceleration, the harder it is to find that object. And we've shown that these accelerations can cause a lot of on-sky motion. This is a plot of the change in on-sky position in arc seconds, which is a terrible unit that is 360th of a degree. There are 60 arc minutes in a degree, 60 arc seconds in an arc minute, because why would you do this in a time format? But regardless, this is the distance in on-sky location in arc seconds for 50 years for one of these dark comets versus gravity only, and then if I've added a non-gravitational acceleration comparable to the dark comets. And what you can see is that you can get, especially for a large A2, which some of them have, you can get uncertainties as large as 10 to the 4 arc seconds, which is like 10 degrees. And you're not going to say it's the same object if you see it 10 degrees away from where it was. The spikes here, by the way, are where this object gets close to the Earth, because it moves in position pretty consistently across its orbit, but when it gets close to the Earth, the angle change goes up quite a bit because the distance goes down. And so you're going to see it at the top of these spikes. And what that means is that you can fail to link up these observations. You can see an object, 10 years later see it again, and misidentify it as a different object. And you can do this to, depending on what the non-gravitational acceleration is, as many as 10% of objects can have this process happen to them, where you fail to find it later. And what that means is that the near-Earth object census is going to be strongly biased by this. You're going to be double counting objects. You're going to be thinking there's more than there actually are. And you will be biasing all your detections to thinking there are fewer non-gravitational accelerations than there actually are. And this can be a problem for these surveys. We have not gotten access to the Rubin pipeline, so I can't tell you if Rubin does this. But we're working on getting better algorithms to make these matching better in the first place. And it's not terribly hard to do. You just include non-gravitational accelerations. But we're encouraging these teams running these surveys to actually include non-gravitational accelerations when we run this. Now, finally, we will have a very fun opportunity, which is that the Japanese Aerospace Agency has sent its Hayabusa 2 SHARP mission to one of the dark comets. They did not do this on purpose. They just chose this target, and then it was found out that it was a dark comet. So we're very excited about this. This will arrive in 2031, which is well after I get my PhD, God willing. So this is something for after I've already graduated. But this will provide a lot of additional data about these objects. We'll be able to see the surface in more detail. This is the current surface map. That's a pixel. It's not great. You can actually determine what its composition is, if it is outgassing, what that composition of the outgassing is, how rapidly it's rotating. There's lots of things that you can learn about objects with this sort of probe. And so that's going to teach us a lot of additional data. With that, I'm going to leave up my conclusions, and I'd be happy to take any questions.
And we have time for about 2 questions now.
Oh, that was quite long.
Hello. Thanks for the great talk. I have a question about slides, I think 9 and 10.
Okay.
If you go back.
I will go back.
Okay.
Slides 9 and 10.
Yeah, I think.
Let's see how fast I can go.
Okay.
What's up?
I think it was the plots where you had like, oh, this is the probability of being like was it some
Yeah,
Jupiter?
being the probability of being detected at this orbital location. Well, the probability of a near-Earth object being at this orbital location.
Yeah. Okay. So I have 2 questions. One
Yes.
is like, how do you produce this kind of plot in the first place? Like, I assume that this is some kind of like Monte Carlo simulation, and then you define some kind of initial conditions. So if you could like clarify the methodology on that. And my second question is, so you talked about selection effects and why like that's why these diamonds are in like the lower density region.
Yeah.
Is there a way you can define a model for your selection effects and quantify like if this is actually what you would expect?
Yeah, so there's a couple of different things that make this complicated. To first answer your first question, the way we generate these plots is there are models of the sources that near-Earth objects can come from. And what you do is you initialize simulations of objects in those spaces, and then you run them for a long period of time, and every snapshot you take a location of where the objects are, and then you make this heat map out of it. And then what you do is, and other authors have done this, you take large-scale surveys of the sky, and you calibrate the abundances of each of these to match those surveys as best as possible. And with that, you can then get an abundance of each of the sources, and this probability distribution saying, 80% of NEOs are from here. So there's a lot more of these than there are the JFCs. So that's how you get these plots. The modifications that I've made is I've added non-gravitational accelerations into those simulations. This is particularly obvious in the Jupiter family comets one. The non-gravitational accelerations are important because they can move you in parameter space. If you don't include non-gravitational accelerations, you get a sharp cut right here and then right here. And I'll do that on this one too, so you can see. There's a sharp cut here and here. You cannot get an object inside of that from a Jupiter family comets, because Jupiter cannot kick objects with that to those orbital parameters, but they can be kicked to that location and then moved inwards, which is what all this uncertainty is. So that's how you get these. As for accounting for observational biases, yes, and the way that you do this is you take these surveys and calculate the probability that you observe it in a given orbital bin, and then the big important output of this is you say, okay, given that I have seen an object at this location, what is its most likely source? And the calculations that you get from that are that these objects are from the main belt and these objects are from a different part of the main belt, but that's not accounting for the fact that they have ices. I will also say that this is completely expected. You don't even really have to do an observational bias thing to say this. If I plotted all asteroids that we know, they're mostly right here. And this is also the most likely source for them. This is the highest probability you can possibly get of finding an asteroid in this location. And all the ones we know about are right there. That's where the Earth is. We see things that are close to us. And so to answer your question, we know this is observational bias, and we can account for it, and we have accounted for it. And that's how we get these abundances in these locations as well.
Final question.
Did I go quite long?
One on your right here.
Hi, my name is Drew. I'm a PhD student in aerospace engineering at Purdue University. So, Aster, very nice talks. It was really cool stuff. I'm curious on kind of 2 points. Mm-hmm. One, can you speak a little bit more about the potential for dark comets to deliver the right volatile amounts to the Earth compared to maybe, say, like the Kuiper Belt objects? And then 2, have we been able to do any spectroscopy on some of the trails of the dark comets to determine their compositions, and if that does a better match with what we would expect for the Earth volatile delivery?
Absolutely. So the issue with volatile delivery is not as much amount. You can do that with one reasonable size object. The Earth does not have that much water. The bigger issue with Kuiper Belt objects and Oort cloud objects is that the isotope ratios are wrong. They are completely inconsistent with the isotope ratios of the Earth's water. And so it can't have been the majority source, because then the isotope ratios will be different. And so the dark comets are, I cannot say that they definitely did deliver water to the Earth. I can say that it has not been ruled out, and it's quite possible, because these are volatiles that are near the Earth. They could have been, these were likely more common in the early solar system, because most asteroids were in general more common in the early solar system, and it's quite possible that they have the right volatile ratios. As for spectroscopy, we can't do any spectroscopy. We can do it of the actual color, and the color looks like a D-type asteroid, which is, actually, sorry, it looks like an X-type asteroid. And I'm going to be completely honest, I do not recall what an X-type asteroid is. I have always hated asteroid colors. We cannot do spectroscopy of their coma, because they do not have one. And so we would love if we could detect the material coming out of it and do spectroscopy of that and find the compositional lines, which we can do for comets, but we can't do for these because we fully just cannot see the coma. We have requested that JWST take a look at it because they could do it, and they said no twice. So if JWST accepts us, gives us time eventually the third time around, then we can maybe get something. But until then, we're sort of holding out hope for Hayabusa 2 Sharp. All right, I think that's time.
Okay. I want to thank Aster again for presenting today. Thank you very much.